This is the 43rd lecture in a class on single agent search, and we're going to continue to look at constraints in this video. And particularly, we're going to look at a method called swamps. And this is not going to be a long video, but I just wanted to give one more example of a way that constraints could be used and show how they can be effective during search. And swamps there's a number of different versions of this work, but they're a relatively simple idea. They're published by Nir Pochter and his colleagues about 10 years ago, but they're very easy to compute. And if you're like doing multiple searches, you could even do them online. And they're similarly effective to many of the approaches that we've looked at here. But I just wanted to give one more flavor of a different type of constraint that can be used. And the idea of a swamp basically is we're going to keep, at a minimum, we'll keep one number per state, which is going to be a group of states that this state is part of. And then we're going to keep a table that basically says what groups of states, so this is like an abstraction method, you would need to go to when you're going to particular goals. And so there's a number of variants of this. There's hierarchical swamps and regular swamps. So let's start out by looking at regular swamps. So regular swamps, in particular, let's look at a map here that looks something like this. And what we notice here is that we have a region at the top, we have a region at the bottom, and then there's a big room in the middle here. And the observation that we can make is that if we are at the top of the map and going to the bottom of the map, so if our start or goal are out here, then we're going to be basically following a narrow channel through the map right here. Put in terms of reach, so reach again is talking about, the start and the goal have to be within some radius. The reach of these states is going to be the highest of any states on the map, because for these states right here, these are the only ones that get you sort of from this side of the map to this side of the map. So a state in the middle here is going to have the highest reach, and then it'll be decreasing going down here. But any of the states, once we get off of that corridor into this area right here or into this area right here, these states can only be on shortest path to states inside here. And so swamp is basically an area where so a basic swamp, not a hierarchical swamp, but a basic swamp is basically an area in the map where the only reason you would go into that map is if the goal was in that area. Okay, so swamps are they're a region in the map that you only enter if they contain the goal. Okay, so given that definition of a swamp, what we can see here is there are multiple swamps in this map, but let's mark some of these. So in particular, this region down here is a swamp because in that region, I'm only going to go into that area if the goal is there. Okay, so how does that work? Well, what's going on here, right, is that if I'm at any other point in the map, so we think about, if we're in this region here, where could we go? So if we ignore this area right here, then the shorter path to anywhere down here is going to go this way. The shorter path to here is going to go this way. The shorter path in here, of course, it's just going to go directly there. The only reason that we would have for going into this region is if the goal was there. And similarly, we could have another region here, or there would be another region here that would be another swamp. And we get the exact same reasoning here. Now, so interestingly, right, if the start is in here, then I'm able to search out of here, but I'm never going to go into a swamp unless the goal is actually in that region. So with a swamp, what we're going to do is we're going to label each state with a ID, which is going to be the ID of the swamp. And so the very basic version is that you could then say, well, I'm never going to go into that region unless the goal is there. And there's additional swamps we could have here. For instance, basically for a map like this, what we're going to see is basically every corner of the map. There's actually multiple choices down here. Clearly forms a swamp. But what we could do actually is that we could actually say that this whole region here is also a swamp. So there's a question of how I want to build that. And similarly speaking, at the bottom here, we could say, yeah, this region down here is a swamp. I would never go down here unless the goal is in that region. Okay. And then we can go further, right? Because we could now start to combine swamps together and say, well, given that one area is a swamp, we might be able to make a higher level reasoning about other areas, or we can merge them together. And, for instance, if, so if you think about it, this is being a little bit silly here, but if we think about it, I'll mark off a large area here, right? In some sense, I could actually take this whole part of the map right here and say, well, this whole region here is also a swamp, because if I'm, if the goal isn't inside here, then I should never go inside. Of course, that only leaves this one portion here, and then you'd move back and forth, that you could only solve problems back and forth inside here. But you could imagine in a much bigger map that we might identify these initial regions that are swamp-like here. And then once we have those, these are basically dead ends here. Well, once we have those, this area inside here, again, consider that the map continues out here, then this area basically becomes a swamp only once these other places have been identified as swamps. Now all of this becomes a swamp, and so you could work your way up hierarchically. Okay, and so the very basic version of this is basically you just say, well, here's a region where you'll never go into that region unless the goal is there. There's a very, very similar idea that was proposed by Yngve Bjørnsen and Kari Halderson back in 2006. So the original Swamps paper, these were published between 2008 and 2010. But there's another idea that was published prior to that, which was very, very similar, which is the idea that if we can partition our state space up, and maybe I might be able to come up with a better partitioning scheme than I would have with the swamp partitioning scheme, especially if my maps have certain structure to them. I can start to represent where are the places where I need to go at a high level. So if you think about, like, I can label each of these rooms here. Practically speaking, each of these rooms we could consider to be a swamp. And so we could be coloring each of these rooms in different location, in different colors. And when we're doing a large scale pathfinding task, we would be able to say, well, look, if well, let me show you. I'm going to finish labeling these, and then we can go into something that's even a little bit more complex here. But what we're doing here ultimately is we're building an abstraction of the map. And the abstraction that we get here is specific to, well, it's one type of abstraction. And there's different type of abstractions that have been built for different types of environments. But let's see, here's our last region here. Okay, so we just have some method that's going to divide our space up. So now we can go a lot further here. And these are basically very similar to the idea of swamps, but now we get to start thinking about, for any pair of regions here, for any pair of regions, if I want to go between these regions, I can think about, well, what areas would I go into or not go into? So this gets to, and this is what the hierarchical swamps are doing, something very similar to this. It's not just saying, like, I wouldn't go into this region unless the goal is there. So the yellow region would not be a swamp because I use the yellow region to transport between two other regions in the map. But what I would see is that if you give me any two locations in the map, for those two locations, I'm actually in this map only going to go to that location, the yellow location, and then wherever the goal happens to be. So I can also do pre-computation. Again, this would be something like hierarchical that say, if my goal is here, I start to merge these together. So now I could start to look at the start and the goal, and I could say, well, if you're going to go on the start and the goal, then here's, for any particular start and goal, I could talk about all possible regions you might go through. And I'll be a little bit careful here. So I'm going to modify this map just slightly. And the way I'm going to show this, let's see if we can. So if we go down here and we look at this wall that I'm uncovering here, I'm going to open up another door inside here. And when I open up another door inside here, and maybe even up at the top here, I could open up another door. These regions are larger regions, and at this point now there's multiple ways that I could get through here. So depending on where my start or my goal is, I might be taking a shortest path this way. If I'm coming here, I might take a shortest path this way. And so then if I've divided the rest of the world up into different regions, so let me just say maybe I have another region that's sitting here. I might have multiple answers here, right? So I might come through here and only be in the orange, the yellow, and the pink, but here I might go orange and purple and pink. So in more complex maps with more complex topologies, I could be thinking about these abstract state spaces and where I would be going, what regions I would be passing through. And so this is, as I said, I'm not going to do a really long video here. And again, I'm not getting into a lot of the details, but I'm just pointing out that this idea has, people have looked at this quite a bit over time. And there's even some work that goes back to a thesis at Stanford. This is probably 20 years ago. That was sort of saying, so this is getting a little bit off topic here, but for instance, saying that if I have a map that only has a choke point here, then I actually know like that I can basically subdivide this path into two pieces on either side of the choke point. But what we see basically is there's a lot of work that gets out of the standard space of looking at heuristics we've been going so far in the class and starts looking at other constraints. So swamps, it's a region that I only enter if it contains the goal. When we look at hierarchical swamps and these other approaches that have been looked at here, what we start to do is we think about abstracting the map into regions, and we start thinking about like what are the shortest paths look like in this abstract space. And we start to be able to, again, prune these other places that wouldn't be part of these abstract locations. We can think about if my map has subdivides in it, how can I path through these subdivides? When I've divided the space, I can basically make two independent problems out of here. You know, if I have two openings, then I can make sort of like four independent problems. And so we're going to get to how then these ideas will build up into even higher level ideas in a following lecture that are going to start to be able to get us not only sort of slight improvements in search, so something like swamps are able to prune out some pieces in our state space, but we're going to start to get into ideas that will allow us to start to get very, very fast shortest path queries. So this last piece I wanted to put here in this series of looking at constraints sort of here is pointing towards some of the high-level structures that exist within maps that we might find or that we might even be able to label abstractly. And what we're going to do is we're going to push these in two directions. We're going to push them in one direction into very suboptimal search, or potential of suboptimal search, but very, very fast search that's going to be suitable for dynamic maps, dynamic problems that are typically faced by the games industry. And then the other direction that we're going to go is into looking at finding extraordinarily fast shortest path queries, where I can basically immediately extract out the shortest path. And these are going to be built on more of the idea of constraints or pre-processing the map than on the idea of building heuristics. And so, as I said, this would be short, but we'll continue from here looking at how we can now do a lot of real specialization coming out of these sort of more general ideas here. These ideas are not like these ideas were, I just want to be careful. Like the idea of swamps was not, some of the stuff I'm going to talk about later was probably developed completely independently, or certainly was developed completely independently from some of the hierarchical methods I'll be discussing. But I just want to say, like, in terms of the ideas themselves, they're very related to each other in terms of building up the ideas of what sort of structures I have, and then being able to exploit those structures in a state space. So we will continue that in the next video.